I will be giving lecture on the Maxwell distribution law of velocities. So, let me start it. Actually, before coming to the topic, let me tell you what are the random quantities and the probability. First of all, I should familiarize with these quantities, then I will start what is the derivation of Maxwell distribution law of velocities. Random quantities and probability. Let us consider a small region in the space occupied by an ideal gas. Molecules of the gas move arbitrarily. We cannot specify the time when an individual particle will be located inside this region in the course of its motion. Hence, the location of a particle in a given region of space is an random event. The motion of microparticles like electrons, protons, photons, etc., is described by quantum mechanics, not by classical mechanics. It is so, it is impossible in principle to predict their locations as well as their dynamics simultaneously, which is nothing but the uncertainty principle between position and momentum. Hence, the position of a microparticle in a given region of space is a random event by nature. Suppose, as we know, according to the uncertainty principle, any two conjugate variable cannot be measured simultaneously accurately. Suppose, if I can localize a particle, suppose if I know the position of a particle, then its momentum could be completely uncertain. So, that is the reason simultaneously if I know its dynamics, suppose if I know its momentum, then its position is completely uncertain. So, that is the reason the position of microparticle in a given region of space is a random event by nature. Thus, most of the events in a many particle system are random. The coordinates and velocities of the molecules in a gas are random quantities. In order to describe the behavior of random quantities, we introduce the concept of probability. In fact, in our lecture, we will derive what is the probability of finding a molecule having velocities between v and v plus dv in a gas. So, that is the reason, that is the quantity we are going to calculate. Now, let me start what is Maxwell distribution law of velocity. We consider an ideal gas in a vessel of volume V. A gas consists of large number of molecules moving arbitrarily in all directions with all possible velocities ranging from 0 to infinity, which are changing continuously in magnitude as well as directions due to collision with other molecules. This is the first assumptions of the derivation of Maxwell distribution law of velocities. That means, the velocities of the molecules in a gas can will be from 0 to infinity, they can take any velocity. Infinity means maximum limit of the velocity of light is obviously velocity of light in free space, but as we have already told in the lecture series of kinetic theory of gases, that will not introduce any error. So, that is the reason, for the sake of the calculations, we are saying the velocity of the molecules in a gas can take values from 0 to infinity. The distribution of these velocities is governed by a certain law known as the law of distribution of velocities, which known as the Maxwell distribution law of velocities. Obviously, it was derived by Maxwell in 1859. Now, let me start it by assuming n be the number of molecules per unit volume of the vessel, and let a molecule move with a velocity c in an arbitrary directions whose components of along the x, y, z direction are u, v, w respectively, and obviously, the length of this velocity vector c square equal to u square plus v square plus w square, like the radius vector in the coordinate space is r square equal to x square plus y square plus z square. Obviously, the radius is measured from the origin, which is defined as the 0 to x y z. Similarly, here in the velocity space, the origin coincides with the 0 and a point in the x y z plane is u v w. So, c square equal to u square plus v square plus w square. If nu be the number of molecules per unit volume having velocity u, then the number of molecules per unit volume having the velocities lying between u and u plus du is given as nu du. So, this is the first thing. If nu be the number of molecules having velocities u and u plus du, then the number of molecules per unit volume having the velocities lying between u and u plus du is nu du. Okay. When nu is some function of u, then nu du is f of u du. Okay. Then the number of molecules per unit volume having velocities lying between u and u plus du will be nu du equal to n into f u du. And hence, the probability that a molecule selected at random will have the velocities lying between u and u plus du is f u du. Basically, you have to divide the equation 4 by n. So, you will get the probability which is nothing but f u du. We assume that f u is independent of v and w. Similarly, the probability for molecules with velocities lying between v and v plus dv is f v dv, and the probability of finding the molecules having velocities u w and w plus dw is f of w dw. Here we have assumed that these events of u v w, these are independent to each other. Then we will use a theorem in the probability theory that I am going to tell it now. If the probabilities of occurrence of two independent events A and B are P A and P B, then the probability of simultaneous occurrence of two independent event is given by P of A B equal to, it is a product of two probabilities P A times P B. This is the probability multiplication rule for independent events. It can be generalized for any number of independent events. Thus, for example, the probability of simultaneous occurrence of independent events, let us say A B C, is defined as P of A B C, which is equal to the product of the probability of individual events. So, equal to P A into P B into P C, etc. So, now we will use this probability theorem in our case. So, let us say, hence the total probability that a molecule can have the velocity lying between u and u plus du, v and v plus dv, w and w plus dw equal to f of u times f of v times f of w du dv dw, which is just the product of the probabilities, three independent probabilities f of u du, f of v dv, f of w dw, which is the product of the individual probability. Then the number of such molecules per unit volume will be n f of u, f of v, f of w, du dv dw. These molecules are contained in the volume element du, dv, dw in the velocity space. So, as shown in the figure, from this figure you can see that these number of molecules are confined in the volume element du, dv, dw. Now, these molecules have the resultant velocity c. So, the number of these molecules must be n into f of c du, dv, dw. As I have already told you, c is the resultant velocity, which is nothing but the in analogy to the position radius vector in the coordinate space, c is nothing but the c square equal to u square plus v square plus w square, where f of c is the probability for molecules with velocity c. So, equating equation 9 and 10, we get f of u into f of v into f of w equal to some other function which is f of c, which is nothing but the phi of c square, say, where phi of c square is some function of c square. So, for fixed values of c, phi of c square is constant. So, d of phi should be 0. So, if I will take if I will differentiate d of phi, so what I will get? D of f of u times f of v times f of w equal to 0. So, if I will take if I will differentiate them keeping other two values constant. Suppose if I want to take differentiate u, so keeping constant v and w. Similarly, I can differentiate v keeping constant u and w. Similarly, I can differentiate w keeping u and v constant. So, if I will do this simple mathematics, what we will get it? F of f prime u du, f of v f of w plus f of u f prime v dv f w plus f of u f of v times f prime w dw equal to 0, where prime stands for the differentiation, f prime u stands for df by du, f prime v stands for df by dv keeping other two variable constant. Similarly, f of f prime w means the derivative of probability function with respect to w keeping u and v constant. So, dividing the equation 14 by f of u, f of v, f of w, we will get a beautiful equation f prime u by f u du plus f prime v by f v dv plus f prime w by f w dw equal to 0. Now, for fixed values of c, we know that u square c square equal to u square plus v square plus w square. If I will differentiate this thing for a fixed values of c square, d of c square should be 0. That means, u du plus v dv plus w dw should be 0. Now, I have two equations. One equation is obtained by differentiating d of phi equal to 0, and second equation by demanding for a fixed values of c square, d of c square equal to 0. So, I got the two differential equation. From there, I have to find out what is f of u, what is f of v and what is f of w. So, I have two differential equations, from there how to solve f of u, f of v, f of w. This is a new method which is known as Laplace's method of undetermined multiplier. So, what to do? Suppose if you have one mother equation which is f prime u du, just let me show you, just equation 15, this is the mother equation. Other constant equation is equation number 16. So, what is the rule to do it? If you have 2-3 constant equations, so you multiply one constant to each constant condition and then you add with the mother equation and then you demand that the coefficient of each variable will be 0 separately. Let me start it, how to do it. So, f prime u by f u plus beta u du plus f prime v by f v plus beta v dv plus f prime w by f w plus beta w du equal to 0. So, since I got this equation, then I will demand that since du, dv and dw, the coefficient of du, dv, dw, since they are arbitrary. So, the coefficient should be 0 independently. If I will do it, what I will get it? I will get first equation f prime u by f u plus beta u du equal to 0. That means, f prime u by f u plus beta u equal to 0. Similarly, f prime v by f v plus beta v equal to 0 and f prime w by f w plus beta w equal to 0. So, I got 3 ordinary partial differential equation. if I will solve these 3 ordinary partial ordinary differential equations, or not this partial differential, this is 3 ordinary differential equation. Once I will solve these 3 ordinary differential equation, I will get the solution f of u, f of v, f of w respectively. Once I got it, then I will multiply f u, f v, f w to get f of c square. Okay. This is the algorithm of our mathematics. Okay. So, let us do it. So, f prime u by f u equal to minus beta u, f prime v by f v equal to minus beta v, f prime w by f w equal to minus beta w. So, from the first differential equation, if I will solve it, I will get log of f of u equal to minus half beta u square plus log a, where a is the integration constant. If I will rewrite it, then I will get it f of u equal to a e to the power minus beta u square by 2. Let us say beta by 2 is some other constant b. So, I will get a e to the power minus beta u square. So, where a and b are the constant. Similarly, I can solve other 2 ordinary differential equation. So, I will get f of b and f of w, which will look like f of v equal to a e to the power minus beta v square, f of w equal to a e to the power minus beta b w square, where b is nothing but the beta by 2, where a is nothing but the integration constant. So, once I got f of u, f of v, f of w, then I can define the combined probability having the velocities u and u plus du, v and v plus dv, and w plus dw. So, hence the number of molecules having the velocity component lying between u and u plus du, v and v plus dv, w and w plus dw is given as the product of these 3 terms, which I will get dn equal to n a q e to the power minus b u square plus v square plus w square du dv dw. So, this is the famous Maxwell distribution law of velocities, where du dv dw is the volume element in the velocity space. In the spherical polar coordinate system, in the velocity space c theta phi, the volume element can be written as du times dv times dw equal to c square dc sin theta d theta d phi. As we know, in the coordinate space, the volume element is defined as dv equal to r square dr sin theta d theta d phi. Only difference is that r will be replaced by the resultant velocity vector, which is c. Okay. So, if I will substitute the volume element du dv dw in the equation 23, we will get this dn equal to n a q e to the power minus b c square dc sin theta d theta d phi. So, this is nothing but the number of molecules having velocities lying between c and c plus dc, theta and theta plus d theta, and phi plus d phi. If we will integrate this equation for theta 0 to pi, phi 0 to 2 pi, what we will get it? We will get dnc equal to n a q e to the power minus beta c square dc 0 to pi sin theta d theta 0 to 2 pi d phi. What we will get? 4 pi n a q e to the power minus b c square dc. This is Maxwell distribution of law. It gives the complete knowledge of the gas only in the statistical sense. So, now let me discuss this thing. So, if we will rewrite this equation in terms of some new variable, then things will be clear, things will be much easier, much clearer. So, let me do it. From this, the probability of its velocity lying between c and c plus dc is just you divide it by n, what you will get? F of c dc equal to 4 pi a q e to the power minus b c square dc. Let us substitute x, which is nothing but the square root of b c square. Then the above equation reduces to f of x dx equal to 4 pi to the power minus half e to the power minus x square dx, or f of x equal to 4 pi to the power minus half e to the power minus x square. So, this is the probability having some quantity of x, where x is nothing but the velocity, but it is a new variable. So, f of x is nothing but 4 pi to the power minus half e to the power minus x square. This equation is universal in the sense, in this form the distribution function depends neither on the kind of gas or nor on the temperature. So, now if you will plot f of x versus x, a curve is shown in the figure. From this figure we will obtain the following information. So, if we will plot f of x versus x, the curve whatever we will obtain, I will get the following information by plotting this curve. So, I will tell one by one. The total area between the curve and the x axis gives the total number of molecules in the gas. So, this is the definition of integration. Integration f of x dx a to b will give you the area under the curve, which is nothing but the result. Okay. The shaded area, which is shown in the figure, gives the number of molecules having the variables between x and x plus dx, or you can say in terms of velocity, shaded area gives the number of molecules having velocities some c to c plus dc. The values of f x corresponding to any values of x gives the number of molecules with velocities x equal to square root of b c square. The probability when x equal to 1 is the greatest, thus the gas has the most probable velocity x equal to 1. So, from there you will get c equal to 1 by square root of b. So, these are the features of this curve. So, taking this we will compute the constants a and b by normalizing it. Once I will get a and b, then I will substitute it back values of a and b, we will get complete Maxwell distribution law of velocities. Since the total number of molecules per unit volume having velocity 0 to infinity is n, so we will integrate it, we will get the total number of molecules. So, if we will integrate it, the 4 pi n a q will come out of this integration 0 to infinity e to the power minus b c square d c equal to n. So, if I will integrate it, this is nothing but a Gaussian type integration. If you will integrate it by substituting b c square equal to x, so then I will rewrite this equation in terms of new variables. What I will get it 2 pi n a q half b to the power minus 3 by 2 0 to infinity e to the power x to the power minus half dx equal to n. From there, if I will put the value of 0 to infinity e to the power x to the power minus half dx, then I will get a equal to b by pi to the power 1 half. So, as we have already derived from the kinetic theory of gases, the pressure P exerted by the gas is P equal to 1/3 m n by V average values of c square, where c square is the mean square velocity, which is defined as c square average is 1 by n 0 to infinity c square d n c. So, if you will substitute the values of d n c, if you will substitute the values of d n c from this equation, from the equation 26 and substitute it there, then what we will get it average values of c square we will get 4 pi a q 0 to infinity e to the power minus b c square c to the power 4 d c, because c square is already here, another c square will come from d n c. So, c square times c square is c to the power 4. Then again I will substitute b c square x. So, I will rewrite the equation for the mean square velocity is 2 pi a q b to the by b to the power 5 by 2 0 to infinity e to the power minus x to the power 3 by 2 dx, which comes out to be 3 by 2 b. since if you will substitute average values of square velocity c square in the pressure equation. So, we will get P equal to small m times n by 2 V p. However, the ideal equation of state gives P equal to n k T by V. If I will compare these two equations, one is from the experimental result P equal to n k T by V and P equal to m n by 2 V b. If you this equation is obtained from the Maxwell kinetic theory of gases. If you will compare these two equations, you will get the values of B. Once you will get the values of B, then we have already derived it some equation in terms of A and B, you substitute B. So, you will get the values of B. So, in principle we have obtained the constants A and B. So, B equal to m by 2 k T. So, if you will substitute A and B, then Maxwell distribution law of velocities can be written in the form d n c equal to n c d c equal to 4 pi n m by 2 pi k T to the power 3 by 2 e to the power minus m c square by k 2 k T c square d c. This is the famous Maxwell-Boltzmann distribution law. This tells the number of molecules having velocities c and c plus d c. This is a very famous equation, and probability you just divide it by n c, you will get the probability of finding a molecule between c and c plus d c, which is nothing but 4 pi n will go away m by 2 pi k T to the power 3 by 2 e to the power minus m c square by 2 k T into c square d c. Here I should tell some interesting thing. Although it is a heuristic argument, e to the power some any exponential function with a negative e to the power minus m c square by 2 k T, you can think in different way. There are two energy scale in the system. One is, since the system is at thermal equilibrium, so obviously there is a temperature. So, there is one scale which is related to the thermal energy scale, which is of the order of k T. Other energy scale which is intrinsic to the energy to the particle, which is nothing but the simple kinetic energy half m v square. Whenever there is a dominant, whenever there is a competition of two scales, here it is the energy scale. So, there will be always some exponential function will come, which is the ratio of the two energy scale m c square by 2 k T. The quantity f of c, which is I have already told you d n c by n d c, which is 4 pi to the power minus half m by 2 k T to the power 3 by 2 c square e to the power minus m c square by 2 k T is the distribution function of velocities of molecules. So, if you will plot this Maxwell distribution function for 3 different temperature of the system, suppose some temperature having thermal equilibrium at temperature T1, other system having temperature T2 obviously is in thermal equilibrium, other system is in also obviously in thermal equilibrium having temperature T2. If you will plot these 3 figures for the 3 different systems, so what you will see, if you will plot f of c versus c having temperature T1, T2, T3, where T1 less than T2 less than T3, what you will see it, the peak of this curve will shift to the higher temperature. So, physically what does it mean? If the system has system are in a system is in a higher temperature, so obviously probability of finding molecules having large kinetic energy is large, which is obvious, because the square of the mean of the square of the energy mean energy is proportional to the temperature of the system. If the temperature is large, so mean energy will be large. So, that is the reason the peak of the curve will be shifted towards the towards in the right direction. Okay. So, now in deriving the Maxwell distribution of velocities of molecules, we assume that the velocity coordinates are independent, that is we disregard the collision between the molecules. the collision affect the velocities of the molecules. As a result, the state becomes stable or thermal equilibrium. So, that means somebody could ask that why when thermal equilibrium will be achieved. So, in I have given in 2 lectures in the kinetic theory of gases, where I have told somewhere that temperature is a concept, of the isotropicity in the momentum space. Suppose you have taken n number of molecules in a container of gas. Initially their momentum in different directions, maybe it is different, but after some time there will be some isotropic in the momentum space, which is average values of px square should be equal to the average values of py square equal to average values of pz square. This isotropicity in momentum space is known as the thermal equilibrium. But in my earlier 2 lectures, the thermal equilibrium, this equilibrium situation has been obtained by the collision of a molecule between the molecules and the wall of the container, not the collision among themselves. But what Maxwell told, if the collisions will be more, frequent, the system will achieve thermal equilibrium more quickly. Okay. The Maxwell distribution law of velocities corresponds to the state. Boltzmann later showed that owing to collisions between its molecule, a gas will spontaneously pass from a state of non-Maxwellian distribution to a state of Maxwellian distribution. The Maxwellian distribution, sometimes also called the Maxwell-Boltzmann distribution, is an equilibrium distribution. So, now I will tell, since it is a very beautiful laws of nature. So, one must verify the Maxwell distribution law. In a couple of minutes, I will try to demonstrate some experiment through which it has been proved now that this Maxwell distribution is perfect law which is obeyed by the molecules in a gas. Okay. Initially, whenever people have performed some experiment, their experiment in some sense crude. So, their experimental error is not perfect, they matches with the agreement between theory and experiment up to 15% of error. So, more and more refined experiment have been done. Through this refined experiment, now it is confirmed that there is no deviation between theory and experiment. So, in view of the fundamental importance of the Maxwell distribution law in kinetic theory of gases, it was subjected many times to thorough experimental verification. Many attempts had been made, some of them are considered here. So, first experiment in this endeavor is Stern experiment. So, let me start it. Maxwell distribution law of velocities has been verified by the experimental arrangement due to Stern. The principle of Stern experiment can be explained by the given figure, where L is a platinum wire. Let me show you the experiment. This is the schematic diagram of the experiment, where L is a platinum wire coated with silver. The wire L serves as the source of atoms, whose velocity is to be studied. When the wire is heated by an electric current, it emits atomic silver in all directions. The wire L is surrounded by 2 cylindrical diaphragms with narrow slits S1 and S2. These slits are parallel to the wire. Now, this is the schematic diagram of this experimental arrangement. Through these slits, a stream of silver escapes and condenses on the plates P and P prime. Okay. The whole apparatus is enclosed in a highly evacuated glass vessel, so that the silver atoms may not suffer in the collisions in the space. That means, in the within the experimental vessel it is maintained at a very high vacuum, so that there are no air molecules inside, so that while silver atoms, while it is going to the to p and p prime. So, it will not suffer any collision. So, that is the reason it has kept in an evacuated chamber. Okay. The slits S1 and S2 and the plates P and P prime rotated together as a rigid body about the wire L as the axis of rotation. When the entire system is at rest, the silver stream traverses along LO obviously and deposited at O, because it will straight hit to O. So, obviously, it will be deposited at the point O. When the system is rotated around the axis of the wire, so at high speed in clockwise direction, which is shown in the figure, the silver molecules will no longer strike the target at O, but will be displaced from from O and deposited at some point above O. The faster moving molecules will condense near O than slower ones. Thus, the velocity spectrum of silver molecules will be obtained. When the relative intensity of deposit is measured with the help of a microphotometer, the ratio of the number of molecules with different velocities can be deduced and the Maxwell distribution law is verified. However, the result obtained by Stern experiment is quite satisfactory, but still there are some problem in the experiment, because although I have kept it in a highly evacuated chamber, but still that time the vacuum technology is not so in advanced situation. So, you cannot make it completely evacuated. So, that is the reason the agreement between the theory and experiment till up to 15%. So, and this is due to the difficulty in retaining the perfect vacuum in the vessel, as just I have told you. As a result, the Maxwell distribution law has been verified within about 15%. So, thus this method needs to be improved. So, exactly this method has been improved by many scientists. One of the improvements is due to Zartman and Co in 1930, which is described below. First, I will explain Zartman and Co.'s experiment. Zartman and Co. in 1930 have modified the Stern method to study the distribution of velocities of molecules. The apparatus consists of an oven V with an narrow opening A, which is shown in this figure. S1 and S2 are the two parallel slits through which these molecules will go. Above the slits there is a cylindrical drum D, which can be obviously here some section of the cylindrical drum is shown and which is nothing but a circle, which can be rotated in the vacuum about an axis passing through O. It is given in the figure. A slit S3 is on one side of the drum and G is the glass plate mounted on the inside surface of the drum opposite to the S3. Okay. So, you can see that S3 is just opposite to the glass plate G, it is shown in the figure. So, bismuth is taken as the experimental substance. In the earlier experiment we have taken in the Stern experiment we have taken silver, but here they have taken this working substance as the bismuth. So, bismuth is taken as the experimental substance which is heated and vaporized in the oven. A molecular beam of bismuth escaping through this narrow opening is collimated by the slits S1 and S2. So, finally, when the drum is stationary, the beam of the molecule entering into it through the slits S3 strike the glass plate at the same point. Obviously, since it is at stationary, it will go straight and hit the point in the drum. But when the drum is rotated at a high speed, the molecules with very high speed reach the glass plate G first, that is on the right end of G, and molecules with the slower speed reach the plate G on the other end of G. So, after a short time, sufficient quantity of bismuth molecules is deposited on the plate, whose density varies across G according to the velocity distribution of molecules. The thickness of the deposit that is the density distribution is measured by a microphotometer, and this result is obtained by Zartman and Co exactly matches with this, almost matches, not exactly, almost matches with the theoretical distribution which is given by the solid line. If you will plot the intensity versus the displacement S, the this straight line, this connected line gives the theoretical distribution, and this circle, this open circle is the result obtained by this experiment. It almost matches with, except at some high velocity and at the low velocity regime. So, the circles denote the observed density of deposit, while the line represents the theoretical distribution on the basis of Maxwell distribution law. So, the experiment is good which confirms the Maxwell distribution law.